only service level agreement, scheduling becomes very, very difficult. When people say, I'm developing scheduling on cloud computing, and they're only doing 2 tasks, I have seen people actually submitting 2 tasks to cloud and say, I'm doing research on cloud computing, impossible 2 tasks. My laptop can run actually 20,000 workflows in few minutes. How come you use the cloud for 2, 3 tasks, 10 tasks? Impossible. Uh, so scheduling is very difficult. If you're looking at this, we always remain within this area, infrastructure, scheduling for infrastructure only. Fault tolerance becomes very serious issue. I'll talk about it. Uh, Energy becomes very issue. Quality of service becomes very issue. And all of this also depend on the application, the workload type. Okay, so what we talked about, I simply said about public and private cloud without actually telling you exactly what they are. The public cloud, everything is actually provided by third party. So this is the idea. As I told you, that definition for me, at least for me, it doesn't work because third party can provide this part, third party can provide this part, and third party can provide all of it. So unless we actually make clear what is provided in here, we can't really say third party. So there is hybrid cloud uh, and private cloud. You can't see that cloud here, right? Can you? They are clouds. These are clouds. So private cloud is basically is a locked down, only used by owners, and if you link these two, you get what's called hybrid cloud. But hybrid cloud basically, you have your own private cloud. When you need more resources, sometimes when resources become I remember earlier I said resources fluctuates up and down. When your resources actually, when your resource need is more than private cloud, then you can actually send some of them to public cloud. So you buy resources from public cloud instead of buying and adding resources to your own data center. That is the idea of hybrid cloud. It's a mixed usage of private and public clouds, only leasing public cloud service when private cloud capacity is insufficient to do the job at hand. Again, here becomes an issue. Which job you actually send to public? How do you decide? See, the private cloud scheduling before was interesting, but now becomes even more interesting because you need to make sure which job you're sending. Is it the largest job or 3, 4 smaller job? Is it sensitive job or insensitive job? What if all of them are sensitive? How can you do it? How can you leave data here and run the process there? It becomes now very, very interesting in hybrid cloud when you perform the scheduling again or resource management. Now, we still talking about cloud, but the application types that we run on cloud have changed. As you can see, these are new applications, completely different. We did not think about these applications earlier. And these applications include smartphones, tablets, and wearables. And we talk about smart cities, smart TVs, smart fridge, smart cars, all these applications will use cloud computing. And so, as I said earlier, it's in excess of 50 billion uh, devices are expected to hit the cloud in a couple of years. And so, because cloud tends to be one big data center, it will not actually be able to handle this increase. Moreover, these applications are different. Scientific applications are very large. See, if you look at weather crunching application, uh, they have some threshold. You know, they can tolerate 5, 10 minutes, an hour in some cases, delays. But these applications don't tolerate. The latency tolerance is very, very small. Okay? So, what happened? We came up with something called fog computing. Now, fog computing is basically based on, at the center, is based on cloud computing. Okay? Now, this at the end, what you see is different types of applications. Sensors generate a lot of data. And this data is going to cloud, as is now, right? So sensors generate data, we store it in cloud and process it. The same, smart cars, smartphones, and all of this do actually produce data and send it to cloud for processing. Now, what the problem with these devices are energy hungry, right? Sorry, energy. They don't have enough energy. They can die quickly. Uh, their processing capacity is very small. They can't process a lot. So what do we do? The data they send from here to there takes long time. The concept of cloud computing is, why don't we use, there are nodes such as routers, mobile base stations, switches, and so forth between cloud data center and these application producers. Why don't we use them to process this data? Why don't they do actually some tasks? You can send small tasks to them. They can process that, right? Send the result to cloud and then do that, continue. That is the concept of fog computing in a nutshell. So the whole idea is, take the load, if you look at it from there outside, take the load of storage and processing from the cloud to where? To the edge nodes. These could be routers, these could be laptops sitting there. So it could be you are using your mobile phone, right? Instead of doing processing on your mobile phone, it will go to your laptop, because laptop has more energy, more processing capacity, more storage capacity, and it will go there. Now, if you take a lot of photos on your mobile, your battery drains quickly every day. If you take, because keeping them up takes a lot of battery, right? So if you store them on your laptop, because it has more storage there, you increase your battery on your mobile phone. And if you do some processing, you can also pass it on to your laptop, which actually can do that. Instead of actually sending it now, when we read email, we read it where, right? Gmail goes straight to cloud. get the data, and come. Right? So why don't we do it on my laptop? So the whole idea of fog computing in a nutshell is this. It's more complicated than this, but I'm just giving you an idea. If you want to read more, this is the latest paper we publish in this area.
Also, Jamal, some of the papers have even differentiated between the fog computing and the edge computing.
Yes.
They say that the fog is like routers, switches, etc., and edge is the device itself.
Yes, that's what we do actually here. We did this here. So we started here. Many people talk about this. So we did actually say yes. In fact, we went and proposed a different based on what Professor DP said. We proposed a new model, and this new model it appeared in which is this one? Yeah, in Access. This is the new one. So what we're saying is this actually, we combine fog computing and Internet of Everything, particularly for big data processing, because most of these small devices generate a lot of data. Internet of Things generate a lot of data, and we propose this idea of actually putting fog data service in between cloud and the edge fog nodes, uh, and handle all these volume, variety, and velocity of big data characteristics. Okay? Yes, we do actually. If you look at this, we put them out. We do acknowledge fog computing routers, and these they are different than other nodes like laptops and other things that exist in there. For example, base station, mobile base station is different. That's good point.
So
Now,
another big issue is to decide on,
mm,
let's say you are performing the scheduling operation,
yeah.
to decide on which computing, let's say, should go to the fog and which should go to the cloud.
This is another level of complexities. So every time you come up with different platform, you add another level of complexities. Like Professor DP said, should I actually schedule here? If I do, which one of these nodes? And or should I actually go straight to cloud? And if I do, what are the latencies? The application is the one that determines actually right now. And also, the scheduler has to be very careful because of these guys themselves better than these guys, but resource wise, but they are also limited. They are also exposed. They also can fail, right, if you overload them. So a lot of another, when we added another layer of scheduling complexity, as Professor DP said. Uh, in fact, that's the area now we are working on. There is a problem in terms of scheduling here. Another thing that we also found is we do actually reduce a lot of power from cloud, but because we're using this, there is a problem called wear and tear. Okay, a lot because you're using them a lot, they start failing. Okay, so because you have to configure them to use them, right? You configure them certain ways, and this configuration is handling only certain types of messages. Uh, and if you keep sending different messages, it can also reject a lot of jobs as well. This is another work that, as I explained it, particularly to handle the big data issue that we published this year. Now, the whole idea of cloud computing is really the virtualization technology, and it basically gives you a perception of single physical machine, and it also enables different types of operating systems to run on, so you don't care about heterogeneity now, because you only look at the virtual machines, separating applications from the underlying infrastructure. So you don't actually worry about here, because the VMs are going to run, encapsulate your applications, and also it ensures portability of VMs between physical machines, in particular when you want to do VM migrations to increase the utilization level, or to decrease energy, and you can consolidate these virtual machines on smaller machines and shut off the unused ones. Now this is another virtual data center, which is basically mimics the resources here. Okay, this is the idea of now data center as a service. We virtualize the data center as a service. You can see virtual data center here. You can see virtual data center 2 here. The physical resources remain the same, but we can now, instead of actually renting virtual machines as we do now, we can actually rent now the data center itself. This is the idea of virtual data centers. Okay, let me go into workload types that are now run in some of cloud computing. We divide workload types as divisible and indivisible workloads. An example of divisible workload is matrix multiplication, where you have tasks can be actually, you can divide this into task 1, task 2, task 3, this application, and then this application will run on individual nodes. Okay, so you can then, now the only thing is that these tasks have to wait for this one to complete, right? So in fact, you can schedule these two together, task 1 and task 2, or task 1 and task 3, and task 1 and task 2 together, and then these two has to run separately. So all you need is 3 virtual machines. Or you can, if you actually run all of them together, or there is this one actually also sends the output to this one sends the output to that becomes an indivisible workload, because now you can't actually divide them. They all have to run on the same machine. That actually makes scheduling very, very hard. Okay? So at the top, we can actually divide workload always as divisible and indivisible. But it's more than that. There are some workloads, workflow applications, for example. You can see this workflow application, which is very, very common nowadays. There are these works, this T1 can be actually run first, and these two can run in parallel, and these two can run in parallel as well, because they only depend on this, and these two can run in parallel, and then this waits, this runs at the last time. So the scheduler in workflow application usually looks the longest path, right? So that is the time, the most time it takes. That is actually not true. If if all the tasks have the same runtime, and if all the networks are 100% dedicated to send this data, that is true. But because they may have different running time, or maybe they are sharing the resources, and they are sharing also the network. Maybe this is actually scheduled on a machine in China, and this has to send that data to this guy. It takes much more than actually just looking at the longest path. The latest one, which is really uh, this one, but in a different way, all you have is two tasks. One is called map and reduce, which is actually became very famous nowadays. There are only two tasks, but the mappers can be multiple of them. You can have multiple mappers, and you can also have multiple reducers. And this can actually have another level here. You can keep going. So what basically mappers do is these mappers always have to run before the reducers. That's the only constraint. And the mappers will actually take the data, break it into smaller tasks, and return what we call key value pair. So it's like a dictionary. If you know Java or you know Python, it's a dictionary which has value and key, and that returns goes to the reducers, which actually collects those data, those results, aggregate them together, and outputs it. Okay, so now we actually work in this area to make sure that uh, they properly scheduled, because if there is a sync, there is no sync between these two, a delay that is introduced can cause service level agreement to be violated. And you need to make sure that there is a sync when you schedule, map, and reduce together. These are the table of cloud workload types. Most of cloud workload types are web services nowadays. Okay, so this is the most widely used, and then followed by scientific workflow type workloads. A lot of enterprise software, lots of applications from software, and testing also is done. Uh, the second one is called client-centric applications, such as productivity applications, graphics, and so forth. And then mobile-centric applications, which is basically Twitter's, Facebook type of things, and so forth. Again, this is basically what cloud will give you in terms of growing faster if you actually have applications that oscillates, right? So sometimes some applications have scientific applications in particular. What they do is that you take 10 tasks, you run them just to see, to produce the result. If the result is okay, then you keep with another 200. So it keep increasing. Most of these scientific applications that used to be run for a month, 2 months. Now that's the strategy we use. You run first a small one, and if there is a bug, you correct, and then you run until you see the results look, and then you increase the number. So it goes up and down, it grows. So this kind of applications is very good for cloud, And also the peak is sudden peak with performance, and also seasonal trends. Again, most of it is when uh, the fluctuation occurs. This is again with MapReduce, which I already talked. This slide is supposed to be before this slide. Forget about market-oriented cloud, but the cloud architecture, this cloud architecture, we actually developed it in 2012. And we still use this. The first paper we published with Raj Kumar and a PhD student. So I use this on my slide. Raj Kumar also uses it on his slide. He always puts market-oriented. I use dynamic cloud architectures. My work is in a dynamic area. His work is in market-oriented area. But we work together very, very well. So what basically this slide summarizes what cloud computing is all about. At the bottom, you have physical machines, and in between here, you have virtual machines. These virtual machines are allocated to the physical machines. It's not your application, it's not your tasks. When somebody says task scheduling on cloud computing, that's not actually true. It is the virtual machines that gets scheduled on the physical machines. And each virtual machine can have one or more tasks. So in this case, these two virtual machines are mapped to one machine. So what this allows us is that if we find this machine is actually overworking, or we don't need this machine, but we can move these two virtual machines to this machine, and then we can shut this machine off to save energy. So this idea of virtualization is very good in terms of consolidating virtual machines. And also they're good because different operating systems. Your application needs maybe Windows or Linux or whatever. This actually can handle all those heterogeneities. But these ones are actually managed by virtual machine manager here, sitting somewhere here, and monitored. We also have pricing. Again, there is a number of different pricing. I'll talk about this when we get to that in a couple of days, or tomorrow or the day after. It depends on demand and supply, right? So some providers simply use a flat fee. Some providers use what's called spot pricing. I'll talk about all those things when we get there. Accounting component is needed because you have to pay for what you used, right? It's just like metering and monitoring service requests to ensure that service level agreement is met. This one dispatches applications that are accepted. We build a lot. This is not new, but we build a lot on these structures. Like we have now what is called a system that actually checks. I forgot its name. That checks whether admission control. So whether a new request can be admitted or no based on the service level agreements that we have. And if we actually can admit a job, we must make sure that the service level agreement is met, both the previous ones or the other ones. And I actually now work in something called double scheduling, where I can actually basically kick the low service level agreement low priority jobs and put the high priority jobs. So what I'm saying is that if I get someone, customer who always comes back and gives me, buys from me, $20,000, $15,000 of resource, 10,000, 5,000, almost on a daily basis. If somebody who occasionally or just came in and using 3, 4, I can violate the service level agreement of that guy in order to keep this guy. I'm not kicking him off, but I'm just violating his service level agreement little bit to the point where I finish, I'll just tell him free for you. So he won't be, he or she won't be angry. I'll give it to him free based on the work I'm doing. Or I will charge him 10%, 50%, whatever. So we found that most of these people, non-regular users, are very happy even if you give them 5%. So you explore that psychology, but these guys are very hard. Once you lose them, they don't come back. The ones, regular ones, they really need the resources, and they need it now, not later. So I am actually using that dynamic, that admission system as a dynamic admission that works with service level agreement to make sure, so before scheduling, they can say A, B, C, D are possible targets. Okay, and so you don't go and do it while they are running, but you just say these are possible targets that can be delayed, and then re-embarrassed the owners. That's where service level agreement, resource allocator is sitting, and on the top you see a lot of users with a lot of different applications, and in between the users and the resources is what we call brokers that actually negotiate service level agreements, quality of services, and so forth with the end users. I think that's all. Yeah. Thank you very much. I'll be happy to entertain as many questions as you want.
So what is the difference between QoS and SLA?
Okay. Service level agreement is basically when you get your mobile phone